welcome to this webinar on transformation for high-dimensional data analysis in FCS Express. This is the agenda, so the general structure of what I'm going to be doing in the next hour. Basically, I want to give you a very brief introduction about transformation. So why you may want to run transformation and which transformation type are, let's say, the main family of transformation. Then, which are the transformation that you can currently do in FCS Express? And then I want to focus on the new transformation option. So we introduced quite a lot of new features about transformation since the release of FCS Express 6. You see, we introduced the ability to define a parameter scaling, and this can be done for all transformation. We introduced the ability to sample your dataset before running a transformation, and again, this can be applied to all transformation. And last but not least, specifically with regard of t-SNE, we added the ability to change the perplexity. We will see more about t-SNE and what perplexity is. And last but not least, a specific option for SPADE. Again, we will see what SPADE is, which is the different graph layout methods. So let's start. So why you may want to use transformation? Because you have a lot of data. And unless you have a specific gating strategy or a specific cells type of interest, what you may need to do is to open a bunch of two-dimension plot comparing all possible combination of two parameters to really explore your data set. And this is, first of all, is time consuming, but also is not really useful because it's anyway a limited approach, because you will always look at two dimensions at a time. So you will never have a very comprehensive view of what's inside your tube. So what you can do. So the idea is to simplify your data set. Basically, you want to reduce the amount of data. And how can you do that? So ideally speaking, it would be very great to do this while preserving, or even better, while highlighting the information that is inside your data set. So you don't want to lose too much information. So if this is your data set, this is, ideally speaking, this is what's inside your FCS file, for example. So you have a huge list of observation. You see here, in this case, are cells, so your events. And then you have multiple parameters. In this case, I have a data set with 100,000 rows and 20 dimension. So there are two possible approaches that you can use to simplify this data set. So the first one is to reduce the dimensionality of your data set. So you are reducing the number of dimensions. Example of dimensionality reduction algorithm are PCA and tSNE. So PCA is principal component analysis. We will see tSNE later on. A second possible approach is to work on observation. So you are going to reduce the number of rows of your table, of your data set. And this is something that you can do with clustering. So what clustering is doing is to group similar observation together. So let's say that you start with 100,000 cells and you want to create 10 clusters. At the end, you will not have 100,000 rows. You will just have 10 rows in your table. So your table will be much more simple. Example of clustering are k-means and SPADE. So FCS Express gives you the ability to run all those transformations directly inside the software. So principal component analysis, tSNE, k-means, and SPADE. And how can you do that? You can simply go to the Tool tab and click on the Transformation button. So this is the transformation dialog. You see, you can just click on this plus drop-down menu and select one of your transformation, the one that you want to create. You see, we have a lot of transformation actually. I just mentioned PCA, k-means, tSNE, and SPADE, but we do also have two transformation that allows you to integrate your R script. I will not go into any detail, but for people that are dealing with R script, just know that you can let FCS Express run your R script and then re-import the results of that script. So you will be able to deal with the results directly in your layout. Last but not least, we have parameter math, which is in FCS Express since the old ages. This is the one that you may want to use for kinetics analysis, like calcium flux. So I will focus on tSNE and SPADE, but please, if you have any question about any of the other transformation, just send us an email or send a message in the question dialog. So when you create a transformation, the transformation dialog, before it was empty, you see here it's empty, but when you create a transformation, you can easily see that different options are going to appear in the transformation dialog. Oh, I see a question about flow sum. We can try to see later on if you want. We can deal in with private message about that. Thanks, John. So when you create a transformation, you see you have different options. For example, the first one, it's gate option. Gate option, so why you may want to select a gate? Well, because you may want to run your transformation on a specific population, on a clean population. For example, you may want to first remove doublets, to remove dead cells, to remove the debris, or maybe you also want to positively select a population of interest, like T cells or B cells or whatever. So the gate option allows you to do that. Second, parameter option. Parameter option allows you to select the parameter that you want to work with. So someone of you may say, well, I want to work with all parameters. Well, it may not be the case. For example, the time parameter is usually not so useful if you want to separate your population. And basically, the parameter that you want to include and that you want to work with are the one that really can help you in separating the population. So, for example, if you have an empty channel, that will be not useful for what you are going to do. Or, for example, if you are dealing with a pure population of lymphocyte, you may want to exclude forward scatter and side scatter, because you may think that lymphocytes are quite homogeneous in terms of forward scatter and side scatter. Or here is another example. Let's say that your population are all 45 positive. So maybe you can exclude 45 from the list of parameter. But let's say that your cells are all 45 positive, but still you have some cells that are brighter than others. So in that case, if you want to consider that distribution of the antigen, so bright and dim, you can include that parameter as well. So you can play around with parameters here. And the second feature, this is another new features in FCS Express for transformation, it's the ability to apply a scaling to your parameter. So each parameter can be scaled in a different way, and we will see why scaling is so important for transformation. So gate option and parameter option are available for all transformation. The same is true for the sampling option. We will see why you may want to perform a sampling before running transformation, but I can already tell you that usually sampling is performed to speed up the downstream calculation. Then you have the last part of the transformation window contain the transformation option. So those are the transformation specific option. So in this case, the screenshot has been taken from a PCA. And so you see those are the specific options for PCA. If you create a tSNE transformation or a SPADE transformation, you will see different options. but the general layout of this dialog, it's consistent between all transformation. So I want to focus the next part on parameter scaling. So why we need to apply a scaling to parameter when we want to run transformation. So this is the reason. So variance stabilization. This is the crucial point. So we all know that data in flow cytometry approximate a log normal distribution. And this is basically why we always use log or b exponential scale in our plot. So why this is happening? So this is happening because the variance of the data increase with the increasing intensity of fluorescence. So you can clearly see this here. So you see you have, this is CD3 antigen stained with FITC, and I'm looking at this antigen with linear scale. So this is something that we are usually not doing, but for training purposes, it's quite useful. So you see this is the positive peak, which is here on the left. And then you have the negative peak, which is much broad. So in this case, you can clearly see that distances at large value are less significant than distance at smaller value. So this is why we usually apply a log or b exponential scale to our plots in order to make those two peaks, so the positive and the negative, more homogeneous and more comparable. Why we need to do that for transformation? Well, because the most algorithm assume that a particular distance is of equal importance along the intensity spectrum. So the algorithms think that 1,000 of difference here between 6,000 and 7,000 has the same importance that the distance between 0 and 1,000. But we know in this case is not the case. So I have to mention that when we are doing this on plots, we are not really transforming the data. We are just applying a different scale on our plot. So basically, if an event has 1,000 here of value, it will still have a value of 1,000 after applying the scale to the axis. But for transformation, we need to transform the raw data. So this is an example of what's happened when you apply a log scale to a linear data. You see here we have different value, 110, 100, 1,000, and 10,000. And these are the distance between these points. So you see, for example, the distance between 1 and 10, it's 9. But between 1,000 and 10,000, it's 9,000. If you log transform those values, you end up with 0, 1, 2, 3, and 4. And the distance between them, it's much more homogeneous. This is why we want to apply a transformation. And in FCS Express, you can apply any transformation among those. For example, log, b exponential, hyperlog, or arcsine, depending on what you want. So let's have a look at how it is important to apply a correct parameter scaling in when dealing with transformation. So let me first explain how this layout has been created. So I will not go into any detail about which transformation is applied now. I want just to tell you that it's a clustering, that this is my file, and that I've asked the software to cluster those cells in 3 groups. So basically by highs, I would like to end up with group 1, group 2, and group 3. So this is what I'm expecting. I create different transformation, and I did this, as I mentioned before, by going here, Tools, Transformation. You see here I have a lot of transformation. And basically what I'm going to show you here is the same transformation in 1, 2, 3, and 4 different variant. And those different transformation only are only different based on the parameter scaling. So for example, in in this first plot, let me here, I have the results of this clustering transformation when the CD8 and the CD4 are transformed with a B exponential scale. So basically, the software, the algorithm, it's looking at those data in the same way I'm looking them in this plot. So this is what the software is looking. It's seeing. You see B exponential scale, and indeed the results is quite close to what I'm expecting. So 3 different clusters. What happens if I use a log scale? So if I log transform my CD4 and CD8 parameter, and this is what I've done with this transformation. So this second transformation, you see the CD4 and the CD8 are log scaled. So now the software, it's looking at my data in this way. And since log scale cannot handle negative value, the negative value here are not going to be included in the clustering. And this is indeed the results. So I do have 3 clusters here, green, blue, and red, but you see that I'm losing all negative events. So in this case, the log transformation for my parameter, it's not a good choice. What happens if I use a linear transformation for my 2 parameter? This is what I've done here in the third option, in the third variant of my transformation, CD4 and CD8, but you see linear. So the software now, it's dealing with this scenario. And this is the result. So you see, this separation may still be, let's say acceptable, because I have 3 group here that are quite that make sense. But for example, I don't like it because the double negative group contains some positive cells for each CD4 and CD8 subset. So up to now, the B exponential scaling is still the better. It's still the best. Last example, arc-scene transformation. So if I apply an arc-scene scaling to my parameter before running the transformation, so you see here CD4 and CD8 with arc-scene, this is how the software is going to analyze my data. And so it makes sense that it's separate like this. And this is the results when I go back to my plots. So you see, I don't like this separation. So I'm not telling you that the B exponential is always the best. I'm just telling you that this parameter scaling that you are using when you're dealing with transformation, it's super, super important. So based on that, you will have different results. So in this case, the B exponential scale, it's probably the best choice, but you may find data sets that require other type of scaling. This was an example. I also have another transformation here on page 2. And in this case, the organization of the layout is the same as before. So in the bottom row, you see how the software is going to look at the data with different scaling. And in the top row, it's the results of the transformation. You see, for example, with this second transformation, either if you use B exponential or linear scale, you have in both cases quite good results. With log, we are not so lucky. With arc-scene, we are not so lucky. But again, also remember that you have a bunch of different options here. So you may want to play, for example, with the cofactor and see if it improves the separation. So if I go back to my first example, you see here the arc-scene transformation, their arc-scene scaling was not so successful. But maybe if I change the cofactor here, I may end up with a better result. For example, let's say 100. And you see that now indeed I have a better separation. And if I want to reproduce this in my plots here, I can just format the axis and use a cofactor of 100. So this is how the software is. Yes, this is how the software is looking at the way the software is looking at my data. And you see in this case also the arc-scene transformation is quite good. So just the take-home message is that the parameter scaling is super important. The result that you end up with are quite affected by the parameter scaling. So also be sure to use the appropriate scaling when you're dealing with transformation. Okay, so I will close this and I will go back to my presentation. The next topic that I want to deal with and I want to present you is the sampling. So you see here in all our transformation, either k-means or tSNE or SPADE, we have this option, sampling option. So why you want to sample? So sampling, which is also called downsampling or subsampling, it's a way of reducing the number of observation, and I mean, usually you want to do that to speed up the downstream calculation. So how you're performing sampling? So basically you're just keeping fewer data points, but the crucial point is to keep enough points to avoid losing the overall structure of the data. So if you have 1000 events and you just sample 5, those 5 may not be enough to estimate the structure of your data. So you may want to increase that. Which type of sampling methods are available in FCS Express? You see here interval sampling. Interval sampling in flow cytometry is usually it's overlap with random sampling. Basically, interval sampling is sample every nth cells. So let's say that you have 1000 events. You want to sample 100 events from those 1000. You will sample every 10th cells. So either cells 1, 11, 21, 31, or cells 2, 12, 22, and so on. Since your cells have been acquired in a random way from your tube, interval sampling is superimposable to random sampling, unless you are dealing with kinetics analysis, but that's another story. Other two sampling options are target density and weighted density. Target density is also called density dependent downsampling, and this is the sampling that is used by SPADE. So you see that these two sampling type are dealing with density. So you will see those two sampling are really super useful when you want to, for example, increase the chance to sample array population. And we are going to deal with that in a few seconds. Before going into any details, I want to point your attention to this concept, so the density. When you think about density, for example, the density of people in, I don't know, in a given area, or the density of a compound in a volume, you always need to specify the reference. So either is you know, square miles or square meters or liter for volumes. So you need a reference. Which kind of reference we can use for flow data? So in a multidimensional space. And here comes the concept of this alpha parameter. So when you want to calculate the local density, so the density around the data point, you need to calculate the number of neighboring points. So the points that are close to that points, to the point of interest. And neighboring points are defined as any points within a given distance. But again, which is this distance? So how can we define the extent of the neighborhood? So what we are doing in FCS Express is to calculate the median distance between closest neighbor, so one point and its closest neighbor, and we calculate this median using 2,000 randomly sampled cells. So this is the median, the estimate of the median for closest neighbors. Then the distance used to define the neighborhood is obtained by multiplying this median distance, so this value, by a given parameter that is called alpha. And by default, alpha is 5. So it means that the distance that the neighborhood is based on is 5 times larger than the median distance calculated for closest neighbor. And you see this alpha parameter, it's available for both the weighted density method you see here and the target density method here. Because again, it's a way to define how large is the neighborhood. So let's see how the target density sampling work. So again, target density is also called density dependent downsampling, is the one that is used by SPADE, for example. The idea at the basis of this is that we want to achieve a flat density over the whole data set. There are three concepts that are useful to understand this method. So first one, target density. This is quite intuitive, is the density that we want to achieve all over the data space. The local density is the one that we are calculating for each data point. So the amount of points that are around the point of interest. And again, remember that the neighborhood is defined by the alpha parameter. Last but not least, we have this other variable, which is called minimum, or sometimes also outlier density. And this is a way to remove outliers, so to ignore outliers. So let's say that this is the density distribution of a given parameter. So here you have density, you don't have count, but this is just a single parameter. And let's say that we want to perform a downsampling with these two values for minimum density, 5%, and target density, 20%. So this is the final result. So you see when the local density, so here it's higher than the target density. So we are here, for example. The density, it's flattened to match the target density. So you see it's 20%. If the local density is lower than the minimum density, so here, here, and here, those events are discouraged because they are considered as outliers. In the range between the outlier density and the target density, all events are kept, so they are all sampled because, I mean, we cannot increase those density. But basically, this is what you are ending up. And why you want to do this? Because in this case, you are increasing the chance to sample rare events. So not as rare as the outlier, but at least you are not influenced that much by super dense area. So by this basically, and this. So this is how the target density work. Weighted density, it's quite similar in the sense that it's still take into account the density. It's still using the alpha parameter to define the extent of the neighborhood. But it's a little bit simpler since it's just based on a single parameter, which is the weight. You see here, weight. You are not, you cannot specify the target density and the outlier density. So basically, if you set a weight to be a negative value, like -1 or -10, you want to increase the chance to sample rare events. If you use positive weight, like 1, 2, 3, or 10, you will have increased chance to sample abundant events, so events from dense area. Usually you want to increase the chance to sample rare events, so you will usually use negative events. The minimum value for weights is -10, the maximum is +10. So let's have a look at what happened in FCS Express. So this is, let's say, a real example. Again, the sampling option is available for all transformation. In this example, I'm dealing with the R integration, but again, I'm not going into any detail. This is just for training purpose. But the dialog, again, remember, is the same. So you see, you have exactly as before, the gate option, the parameter option, and here we have the sampling option. So first example here, first column, it's my entire data set without any sampling. You see, this data set contains almost 25,000 events. I've just opened a couple of plots here, couple of combination of different parameters, and I've just highlighted 3 population of interest that will be my references along the different sampling method. So you see, I have, let's say, quite abundant population here, 14%. Then I have a quite rare population here, to 0.12, and then an intermediate one, which is 4%. So what I've done here on the right, let me move a little bit, is to sample 2,000 events using 3 different sampling methods. So interval sampling, column 1, target density sampling, column 2, weighted density sampling, column 3. In all cases, I've just sampled 2,000 events, and you see that 2,000 events out of 25,000 correspond more or less 8%. So I've just sampled 1 event out of 12. So what happens if your population is super rare? What happens if it's even less than 1 event out of 12? So the risk is that you will not sample that population at all, or you will just sample few cells. I mean, not enough cells maybe to run your transformation. This is what is happening in this case with interval sampling. So if I just sample 2,000 events out of 25,000, you see each of those population is still represented with the same amount. So this is 13, it was 14, 0.15, 0.12, 4, 421. But if you look at the absolute number, you see here, basically from population 3, which is the rare one, I'm just sampling 3 events. So 3 events may not be enough to run my transformation. So this population may not be considered as much as I want. So how can I handle this? I can either increase the sample size. So I will increase, I don't know, 5,000 instead of 2,000. But again, my transformation will be slower. Or I can just use one of the other 2 methods, like the target density or the weighted density. So you may remember that the target density allows you in defining different variable, different setting. In this case, I set, you see here, I set the sample size to be fixed. So I have unchecked this checkbox. So I can just type the sample size and the alpha. I kept the alpha as by default to 5. And you see that in this case, the software is going to automatically define the minimum and the target density. So basically, it will also automatically define which event will be discarded and thus considered as outlier. And indeed, this is what's happening. So let's have a look at this column. You see the population that was 4%, now it's 25%. So I've increased the chance to sample rare population to the detriment of abundant population. You see that this population was initially around 14, now it's 6. But you see, now I'm also removing outliers. And with 2000 events, the software, the algorithm is removing basically a lot of outliers. And my rare, super rare population, population 3, it's considered as an outlier. And basically, I'm not sampling any events from that. So this is by using the default option. So by defining sample size. So what happens if I check this? So I will be able to specify the sample, the minimum and the target density, and let's see how it's changed. In this case, I'm using 1% as a minimum density and 20% as a target density. I still have no events in my gate tree. What happens if I goes down here? So now the minimum density is 0.001, and you see that now the gate tree, it's the double than in the original dataset. So basically, I'm sampling 20 events out of 29. I'm sampling all the events from gate 2, and you see, to the detriment of the abundant population. So target density allows you to define, again, the way in which outliers are defined, and also the target density. So you can play around and balancing what you want to kept in and what you want to discard. So let's have a look at the last sampling method. So the weighted density, it's the column on the right here. And this is the dialog. You may remember that the weighted density allows you to just define sample size, alpha, and weight. So you don't have the ability to discard outlier. Let's first see if we use weight 0. So basically, what you have with weight 0 is the same frequency of the original dataset. So 14, 0.1, and 4. If you use negative value, you are going to increase the chance to sample rare events. -5. Let's see how does it change. You see now the population 3, which was the rarest one, it's 1.10. So it's 10 times more frequent than in the original dataset. The population 2, it's the same as in the original dataset, and the population 1, again, is pretty much similar. So at this point, we just increase the rare population. Of course, we will have, we are going to lose some other events. I mean, events that are not in those gates. If I use -10, which is the minimum value, you see now the rare population is 1045. The intermediate population is 38 as compared to 4, so it's increased a lot, the frequency of sampling for this population, and we almost discard the population that was really abundant. So now it's 2.6 instead of 14. So those are the way in which you can deal with the sampling. And again, you can apply sampling. You can use all these different sampling options with all the transformation. So this is something that you cannot do with any other software. So basically, you can use target density with tSNE, weighted density with PCA, and whatever. You cannot do this with any other software. Okay, let me close this. Let me go back here. I want to focus a little bit more on two specific transformations. So tSNE and SPADE. So tSNE, it's an example of dimensionality reduction. You remember dimensionality reduction is a way to reduce the number of dimension of your dataset. So you're not going to reduce the number of observation. So you see here, this is, let's say, a definition of dimensionality reduction algorithm. So those algorithm maps high dimensional data into lower dimension. So basically, when I think about dimensionality reduction, I always bring this example. So this, at my knowledge, is the first real example of dimensionality reduction. So you see, we needed to move from 3 to 2 dimension. And what you have to do, what you want to do with flow data or with mass cytometry data or whatever, is to go from 10, 20, or 100 to 2 or 3. And this is what also tSNE is doing. So tSNE, again, try to find a low dimensional dataset that best preserve the distance between the data point in the original high dimensional dataset. So basically, the position in which those events are in the new dataset needs to resemble as much as possible the position in the original dataset, but with slight adjustment. And why we have this ability to make adjustment? Because tSNE, it's a non-linear dimensionality reduction. So for example, here you have a dataset, so FL1 against FL2. If you run principal component, again, we didn't deal with principal component, but you can clearly appreciate that distances are maintained, and then also the overall structure of your population is maintained. While tSNE, you see here, naturally expands dense cluster and contracts sparse ones. And you can clearly see, for example, here, looking at the violet population. So the violet population is sparse. This is the results of a tSNE transformation, and contract sparse one. And you see this, for example, this sparse cluster, the green one, here has more or less the same extent of all the other cluster. So what tSNE is doing is to adjust the position of all your events in a single two-dimension plot, creating these two new parameters, tSNE X and tSNE Y. This is just an example of real data. You see different parameter, and this is the tSNE plot against X and Y. I usually suggest to, let's say, look at this tSNE plot like a map. You see you have different cluster, different highlands of data. Those are all different population. How tSNE works, I want to give you a brief introduction because it will, needs to, for the following step. So first of all, tSNE calculate the pairwise distance between all your data points. So if you have 1,000 data points, it needs to calculate the pairwise distance between all of them. And this is why tSNE is so slow and so resource consuming. If you have 1 million, it will be, well, 1,000 billion of calculation. The second step is to create the new dataset in the lower dimension. And in this step, tSNE is randomly initialized. So I just want you to take home this message. So randomly initialized. This is why tSNE in the original implementation gave different results when it was run twice on the same dataset. Nowadays, we can control this, we can ensure reproducibility, so you will not need to care about this in the future, up now. Then it calculates the pairwise distance in the new dataset, and then it starts to compare the new dataset with the original one. And at every cycle, because you need to know that tSNE it's an iterative process, at every cycle, tSNE refines the new dataset in order to minimize the difference between the two datasets. So the new one in the lower space and the original one in the high dimensional space. So the crucial point here is that it's an iteratory process and you have different cycle, different iteration. And indeed, the number of iteration, it's one of the options that you can deal with in FCS Express. For example, if you run just 10 iteration, you see that you cannot really separate your populations. If you run 100 iteration, you can start seeing different population. If you run for 500 or 1000, you can clearly see different cluster of cells here. By default, FCS Express run 500. You see, usually it's enough, but if you want, you can increase it. You see, in this example, it's pretty much the same. The second option that you can change in FCS Express when running tSNE is perplexity. This was not available in the first release of FCS Express 6, but now you have it. So what's perplexity? Perplexity, it's a guess about how many neighbor points each data point has. So for example, if you set perplexity to 2, you are expecting very small group of cells, each containing very few cells. So basically, you will end up with a lot of small groups. And basically, this is not helping you in analyzing your data. If you increase the perplexity, you see you are basically guessing that group are made of more cells. So you see 20, 50, and 100. And increasing the perplexity will increase the, you will end up with more compact group here. You see that the algorithm is quite robust. So even if you use 20, 50, or 100, in any case, you can clearly see the different cluster of cells. Actually, ideally speaking, if you increase really a lot the perplexity, so for example, when the perplexity is close to the number of events, I don't know, perplexity 100 and you have 100 events, so you are basically expecting to have just a single group. So what you are ending up with is something like the first plot. So having a lot of small group or a single big group, it's basically the same. But if you are in the middle, you see here, you will have quite robust results. The highest number for perplexity in FCS Express is 100. The minimum is 2. Another option that you have in FCS Express, it's the way in which you want to run tSNE. So basically, there are 2 versions of the tSNE algorithm. The first one is the exact tSNE. The second one is called Barsat approximation. So why people develop the Barsat approximation? Well, basically because the exact tSNE was too slow. So exact tSNE is fine if you want to deal with 100 or 200 events, not more. And it's slow because it needs to calculate the distance between every pair. The Barsat approximation, it's of course an approximation, so it's not calculating the distance between every pair of points, but just the distance between each data point and its closest neighboring points. So it's much faster. And it also has other adjustments that make it faster than the exact tSNE. You can balance the amount of approximation using this value here. So it goes from 0, it means approximation 0, to 1, which is the highest amount of approximation. Basically, if you set to 0, Barsat and exact tSNE are basically identical. 1 is the highest amount of approximation. The advantage is that the algorithm will be faster, but of course, your data will be more approximated. By default, FCS Express use 0.5. Nowadays, people are basically always using Barsat approximation because in flow cytometry, you are usually dealing with thousands of cells, not just 100 or 200. This is just to tell you that the developers at the Novo software did a real great job in speeding up tSNE. I made some tests. I ran tSNE in R, so the statistical software, and in FCS Express. And you see, for example, this is the exact tSNE, so it's the super slower version. So if you run tSNE on 5,000 events, with R, you need to wait 25 minutes. With FCS Express, you need to wait 2 minutes. So it's super fast. And even if you are using the bars at approximation, in this case, you can scale up to 50,000 in this case. So you need to wait 6 minutes with R and less than 3 with FCS Express. Of course, if you have powerful computer, those time will be even reduced, but still FCS Express, it's faster. And as far as I know, it's the fastest on the market for running tSNE. So let's see how tSNE is looking in FCS Express. I hope you can see my screen here. You see I have a very simple analysis. I basically have just one gate. I've just opened a couple of plots. I go here, tSNE tools transformation. I can click on tSNE, and you see we have the same dialog that we saw before. I can select the lymphocyte gate. I can select multiple parameter. Always remember the parameter scaling option. I want to select, for example, interval sampling. So this is basically random sampling. And out of 3,000 events, I just want to select, I don't know, 1,000. You see here I have the perplexity, number of iteration, the amount of approximation. When you want to use this transformation, well, it's very easy. You can just drag and drop it on top of a plot and wait. Now 1,000 event, you see it takes probably 4 seconds. And when the calculation is done, you see you can open tSNE X and Y. And here are my different population. You can either gate on a population on the tSNE plot, like in this case. If you want to backgate, remember to apply the transformation also on the backgating plot. And in this case, my population is the negative for all my events. Oh, it's containing a little bit of CD16 here. You see? This is probably CD18. Yes, CD18. Those cells are either CD4 or CD8. Yeah, and those are CD8. You can also do the opposite. So let's say that you want to gate here on a population and to backgate on tSNE, you see? You can also, instead of using a color dot plot here, you can, for example, use density or a contour plot. And the cool part of this is that if you enable the legend, you can also color your events, so your plots, not based on counts, but based on some parameter, for example, CD18. And now I know that my CD18 cells are here. I can do the same then for CD8, for example, and I know that CD8 are here. So this is a very cool way of exploring tSNE plot. So basically the message that I have with this tSNE plot is that I have 1, 2, probably 3, 4, 5, and 6 population. And then I can backgating and explore my tSNE plot. So let me erase this and let me go back here. I will briefly tell you some consideration. Always remember to apply a parameter scaling. And when you want to apply tSNE, to run tSNE on multiple dataset, just remember to concatenate your file. I will not go into any details, just consider that we have a dedicated webinar. We did it a few days ago about concatenation. So feel free to have a look at it or just send us an email. What about clustering? So clustering is the other approach that you can use to simplify your data set. Dimensionality reduction reduce the column, let's say, of your data set. Clustering reduce the row, so reduce the observation. Instead of dealing with 100,000 cells, like in this case, you will end up, I don't know, with 10 cluster, 100 cluster, no matter. The number will be much lower, much smaller than 100,000. So the idea of clustering is to group data in a way that the events in a group are similar together and are more similar than the data in other group. So similar events are grouped together, different events are grouped in different cluster. Basically, a cluster is just a way to assign a classification label. So for each cell, you need to decide if it's belong to cluster 1 or cluster 2 or whatever. A cluster, either cluster 1, 2, or 3, doesn't tell you what's inside that cluster. So the data exploration, it's something that it's performed after the clustering. This is another way to look at the clustering. So this is what I'm starting with. Actually, let's forget about this. This is the final point. So this is what I'm starting with. It's my data set, 100,000 cells, 20 different parameters. If I ask the software to find, I don't know, 20 cluster, 10 cluster, 3 cluster, this is what I end up with. So my table is now only containing 20 rows. For each row, I have different statistic. For example, a useful statistic is the mean of a given fluorescence, a mean calculated among all the cells in that cluster. And for each cluster, you see I have the list of cells that are belonging to that cluster. And how I can analyze these results. So, okay, I've reduced the number of observation, in this case to 20. So I may think about looking at those 20 cluster in a standard dot plot. And I will plot each cluster based on the mean or based on the median or whatever. But at the end, you see, since I'm still dealing with 20 parameter, I will still have to open multiple two-dimension plot. So up to now, I still have some problem with my data analysis. Another way to have a look at cluster is to represent each of them in a graphical way, like a well of a multi-well plates, and then to color each cluster based on a given statistic. For example, this is the mean of CD4 expression. Maybe let's say that this is FL1. So red means CD4 positive cells, green means CD4 negative cells. So at least in this case, I can tell that I have 4 very positive, 4 cluster very positive for CD4. I have a slightly positivity here. So those are probably those 4 cluster. So the 4 very bright and the dimmest one. So this is the general idea of clustering, but the example of clustering that I want to show you, to present you, is SPADE. So let me go on here. So SPADE, it's very smart. So first of all, it's a clustering. So it clusters data into group, but it also reduces the dimensionality of the cluster. So it's not only doing this, but it's also reducing the dimensionality of the cluster. So it's reducing the number of rows and it's reducing the number of columns. This is the results of SPADE. And you see each cluster, it's represented as a circle, as a nodes. But you also see that as compared to what I showed you before, so to what I show you here, here, those graphical representation of cluster are not just aligned into a plate. They are plotted in a, let's say, branch tree representation. And you can see this here. So this is another smart thing that SPADE is doing, because you also have the possibility to see that some clusters are more similar each other than other. So it tells you more information about the general structure of your data. So this is the pipeline of SPADE. You see here SPADE start with a downsampling, and this is a density dependent downsampling. So the one that we saw before in FCS Express is called target density downsampling. Then it clustered the data using a k-means clustering. So it groups similar events together. And then it manipulates the cluster for a visualization purpose. So in this point, so visual cluster in a graph, it's the step in which SPADE is building these three. So the advantages of SPADE are, first, downsampling. You remember downsampling allows you to increase the chance to sample rare events. So this is a huge advantage. Another advantage is k-means, which is quite fast. It has some limitation, but it's quite fast. And then the third step is the graphical representation as a tree. So basically, this third step is this one. So instead of representing each cluster as a lone circle here, similar clusters are linked together by this edge in this minimum spanning tree, and this allows you to have a general idea of the overall structure. Actually, I have to mention that the location of the graph nodes in the plot does not matter. So the only thing that matters is the link between each node. And actually in FCS Express, you can decide different layout in which you can plot your nodes. So if I go back to my example here, let me clean a little bit. So this is the same data set that I was dealing a few seconds ago with tSNE. I will now create a SPADE transformation. So I will select here SPADE. You see the exact same dialog as before. So I want to deal with the lymphocyte gate. I want to include different parameter. Always remember the scaling. I use the target density. I'm going to keep the default option here. So 1% minimum density and 20%. Since SPADE relies on k-means, you have the ability to decide the number of nodes that you want to look for. So in this case, I will just select probably 50. It's enough. It's a very simple data set. But usually you want to overcluster. So you always select a number of clusters here that are more than the number of population that you are expecting. SPADE can be plotted in FCS Express using a heat map. So I will open a heat map here. This message is just going to tell me that the heat map is empty. And this is because I didn't apply SPADE yet. Just drag and drop. You see, this is my SPADE plot. 50 nodes. Each is connected with at least another nodes. You can color each node based on a statistic. For example, by default, it's the arithmetic mean, and you can select the parameter, for example, CD18, and you see, you can clearly see that you have a branch that contains CD18 positive cells. SPADE allows, FCS Express allows you to create a well gate on SPADE plot. So you can just go here, well gate, and I will select this. I will call them CD18, and I will emphasize them on my plot. When you want to backgate, always remember to apply your transformation on your color dot plot. So those are the SPADE. I selected to emphasize that, so they are plotted in a much larger dot size. Probably it's too much. So those are the SPADE. And you can then explore here by selecting other. So this, for example, is the branch containing CD8. And one of the new options that we have in FCS Express is that you can select the different layout method that you have. So this is called, here you see, this is U-shape, it's called arc. We also have, you can select this here. We also have another layout, which is called radio. And you see, basically in this case, the idea is that the tree starts from the center and then it extends from the center. So again, the message is exactly the same, just try to select here the graph layout methods that better that better plots your nodes into the plot. So in this case, we just have 50 plots, so both of them are quite good. If you have a lot of nodes, you may want to play with this. Okay, I think we are almost at the end. Let me we did this. Advantage of SPADE. Thanks to the density-dependent population, smaller population are density-dependent downsampling, the smaller population are emphasized. The minimum spanning tree, it's a good way to have information about the general structure of your data set. Actually, different clustering methods may be used for SPADE. Nowadays, people are using k-means, which is faster. It's not always the best because it's usually k-means, it's good with round shaped population, but this is actually why you want to overcluster. So I hope this presentation was useful for all of you. I see that there have been quite a lot of questions actually. Let me open our page here. Yes, we had quite a lot of questions. Feel free to type in now if you have any question. Otherwise, I just want to direct you to our resources. So if you want to have a look at the other webinar, you can just go here, recorded webinar, and you have a list of all the webinars that we have produced in the past. We have webinar about transformation. This is the first release that we have. We have webinar about SPADE, for example. We also have resources here like tutorial and manual. I want to underline the fact that the manual is really super detailed. If you go here in the transformation, you have specific specific instruction for all the transformation, also for the one that I didn't deal with, so k-means, PCA, R integration. And of course, we are always available for any further question. Just send us an email to support@novosoftware.com and we will be glad to help you. So thanks for your question. I will stay here for a couple of minutes more. Feel free to write us write a question in the question dialog or to send us an email. Many thanks.